Here we go. Which is a core part of system hardening. Increasing open ports, disabling antivirus, regular security updates and patches, and using weak passwords.
I want to say regular security updates and patches.
Yeah. Some of these aren't the hardest questions, but it is a good test in reading them fully because some people just kind of rush through.
Yeah.
You can answer these, but you got to do it quietly. I got kiddos here on vacation, just so you guys know, pretty much in the background. Not able to click on your guys' screen. You guys can't click.
No, I can't click it.
Weird.
Kind of weird.
Okay. Anyways, I'll just tell you guys the answers then, if that's going to be the case. It is yellow.
Yeah.
Weird that it's not letting you guys click. What does EDR provide beyond traditional antivirus? Faster downloads, only signature-based detection, VPN setup, or behavioral analysis and automated response?
I mean, if I had to narrow it down, I'd say it's between signature-based detection or behavioral analysis and automated response.
What do you think, Sally? Yeah, 10 seconds left. Green? I believe green is the answer.
Green, yeah.
Great job, guys. Look at you guys go. What are host-based firewalls used to do? Monitor inbound/outbound traffic on endpoints, backup files to the cloud, schedule system updates, disable multi-factor authentication.
I would say monitor inbound, outbound traffic and endpoints.
Bingo, guys. If it let you guys put in the answers, you guys would be soaring right now. What does infrastructure as code help do? Physically isolate servers, reduce local disk space, increase user privilege, or maintain consistent deployments across cloud providers? What do you think? Kiddos are guessing along too.
Let's say. Probably guess green.
Bingo. Great job, guys. If need be, I have the videos posted and some notes and everything as well. What do serverless architectures focus on? Individual application functions, full server management, physical device air gaps, or VLAN segmentation? Sorry, I wrote this at like 1 a.m. last night after working.
Oh.
Sally says red.
Yeah, I would say red.
Red.
Because we're considering serverless architectures like cloud computing most of the time.
Yeah, because we watched, to put it into perspective, we did hardening techniques, cloud infrastructure, and network infrastructure last week.
Yeah.
You guys are nailing it. What do VLANs provide? Behavior and malware detection, logical separation of devices on the same switch, cloud IAC deployment, or end-to-end encryption. Sally says blue. Pete also says blue.
Yeah, blue. For virtual local area networks.
Great job, guys. What does the shared responsibility model in the cloud entail? Customers handle everything. Security duties are split between provider and customer. Vendors manage physical air gaps. Providers handle everything. This is blue again.
I'd say blue.
Bingo. Yeah, you'll see it as like a. We can look at a picture of it later. Just a little graph, colored graph that shows who handles what.
Yeah.
What can microservices in the cloud help with? Disabling EDR, remove need for encryption, improve resilience and scalability, or increase attack surface area. Yellow. What Sally says.
I put in the answer.
Say that again?
Oh, I just put in the answer. I just put in improve resilience and scalability.
Excellent. Great job, guys. We got some points.
Hey.
What is changing credentials and enabling MFA on management interfaces considered? Key security best practice, optional and rarely needed, required for open ports only, or only for cloud service? That's red. Excellent, guys. Were you about to ask something before I started reading it?
No.
Oh, okay. I just wanted to make sure I wasn't trying to interrupt.
No, not at all.
What does port management help with? Disabling host-based firewalls, break VLAN segmentation, reduce attack services by closing unnecessary ports, or increase network traffic.
I would say reduce attack surfaces by closing unnecessary ports.
Make sure Sally had answered. She did. Great job, guys. To the scenario be it, please. Company deploys a new app using IAC across AWS and Azure. What is the key benefit? Physical air gap isolation, automatic malware detection, disabling endpoint security, consistent and repeatable deployments. It always says green.
Yep.
Bingo. An admin notices a switch misconfigured, allowing too many devices on the same VLAN. What is the main risk? Reduced patching needs, improved serverless performance, lateral movement by attackers, or faster VPN connections.
Lateral movement by attacker.
Ellie says that as well. Great job, guys. The cloud provider patches servers, but customers manage IAM and encryption. What is this an example of? Shared responsibility, IAC deployment, microservices usage, and serverless architecture. Sally says red.
I'll say share responsibility.
Great job, guys. Almost done. Two more. A laptop with sensitive data stolen. Which mitigation would have minimized risk? VLAN segmentation, full disk encryption, disabling firewall, or SDN implementation.
I would say full disk encryption.
Excellent, guys. Last one. Let's get to 100% for both of you. Company isolates development, production, and management networks using SDN and microservices. What is the main goal? Removing the need for MFA, reducing endpoint protection, precise segmentation and security control, or faster open port scanning. Oh, it says yellow.
I mean, security goal was said right.
Excellent, guys. We can look at the podium.
Huh?
I said we can check out the podium here. Sally couldn't put in answers. Glitching. All right, guys. Yeah, you guys did a great job. So I got several videos for us today.
Good.
All right, I'm gonna get this started. If you guys have any questions or anything, just say something or post in the chat, and I can pause it.
Okay.
Otherwise, here we go.
If you ask an IT professional where the safest place to store data might be, some might tell you that your on-premises infrastructure is the safest. Others might tell you a more secure environment is in the cloud. Both of these, of course, have their advantages and disadvantages when it comes to security, but of course, there are many other considerations to take into account. If your security is in the cloud, then it's centralized with all of your other cloud-based services. There's no hardware that you have to support, there's no separate data center that needs to be cooled and staffed, and the third party providing the cloud-based services also provides the security. If you have your own data center, then all of your security technologies are local and on premises. But this also means that you have to support all of those systems, which of course has a cost associated with it. From the attacker's perspective, they don't care where this security happens to be. They're working to circumvent and get around this security regardless of whether it's in the cloud or on premises. If everything is in-house, then you have complete control over the decisions made with the security, the options that are available to install, and you manage the entire process. In most on-premises infrastructures, there is an IT team that handles the management and maintenance of all of these systems. The staff that's managing this on-premises security are well-trained, professional, and cost more than something that might be in the cloud. But of course, when you have your own data center, you have complete control of all of the data and all of the systems. If you want to make a change to an existing system or modify a security posture, you simply do that yourself. You don't have to call a third party or access your cloud provider to make that happen. However, if you'd like to bring additional equipment into the data center, there are obviously costs for purchasing the equipment, and it does take time to purchase, configure, and install this technology. In most organizations, the technology is decentralized. You might have multiple locations for your organization. You might be using multiple cloud providers. And of course, there's more than one operating system that's running on all of these systems in your environment. From a security perspective, this becomes challenging to manage. Having all of these different systems in so many different places create a challenge for IT professionals to maintain the security of their data and applications. To address these challenges, many security professionals will create a consolidated management view of all of their systems from one single console. This allows ongoing monitoring of every user, every device, every application, and anything else that's important to monitor from a security perspective. You might get consolidated alerts brought to a single console. There might be a consolidated log file analysis so you can easily search for information regardless of where it might be in the organization. And there might be a global process for maintaining systems and keeping everything up to date. Having this centralized point where you can view the entire organization does provide additional visibility, but it does create a single point of failure. If you lose the console, you effectively lost your visibility to what's going on with your security. And as your organization grows larger and larger, that system begins working more and more. You may need additional storage space to handle the increasing number of logs, and you might need additional CPU power to be able to manage the additional alerts and alarms that might be received. Virtualization is also a significant technology that's running in practically anyone's data center. This allows us to run Windows, Linux, and other operating systems and be able to build these systems instantly and tear them down when needed. One challenge with a virtualized environment is that each individual virtual machine needs to have its own operating system. The architecture starts with the infrastructure or the physical device that everything will run on, and then there's software that runs on top of that called the hypervisor. A hypervisor's job is to manage all of the resources between the separate virtual machines running on that system. Each virtual machine requires its own guest operating system, and on top of that guest operating system will be the applications that you need to run in your environment. Looking at this diagram, you can probably see where different inefficiencies might be. For example, let's say that every guest operating system on this hypervisor is all running exactly the same OS. Maybe this is the same Linux operating system or the same Windows operating system. Even though it's all the same OS, you still need to run 3 separate instances of that operating system, even though they're all identical to each other. To address some of these inefficiencies, some organizations are moving from a virtualized environment to a containered environment. Containerization is a way to also have multiple applications running simultaneously, all on one single piece of hardware. The container in this containerization is the applications that sit on top of the container software. That container has everything you need to be able to run that application except for the operating system. The containerization software manages this relationship between the operating system on the device and the application that's running on top of it. This effectively allows you to swap applications in and out, especially when those applications are all sharing the same host operating system. And similar to virtualization, all of these containers are isolated from one another. Each application can only see the application that's running in that individual container, which makes it very efficient to be able to remove or turn off a container and replace and add others. You'll also notice that each of these containers is referencing a single host operating system that's running on this infrastructure. So generally, these apps have already been designed to run on that single host operating system, and that means that everything that's on that particular system might be running inside of Windows. You might have a separate containerization system that would support applications running in Linux. So to compare a virtualized environment versus a containerized environment, you can see they all start at the bottom with hardware that everything is running on. That is the infrastructure itself. This changes a bit as we move up through the stack. You can see that a hypervisor is what sits on top of the infrastructure in a virtualized environment. But for a containered environment, we've got a host operating system that is running on that infrastructure. On top of the host operating system is the containerization software. One of the most popular is called Docker, and that is the software that then manages all of these different apps that are running on the system. In a virtualized environment, our guest operating systems are running as separate entities on each virtual machine. There are, of course, advantages and disadvantages to both of these types of implementations, and you should find the one that works best for the types of applications and deployment model that you have. A relatively new categorization of infrastructure devices is called IoT, or Internet of Things. These are devices that are designed to be integrated into your network and support some of the features and services that you use on a day-to-day basis. For example, you might have sensors in your home or business that are monitoring the temperature and managing the heating and cooling. Or your offices may have an automatic lighting system using Internet of Things. At home, Internet of Things might look like home automation tools, garage door openers, and video doorbells. You might be wearing an Internet of Things technology if you have a smartwatch or some type of health monitor. And at work, you may find that Internet of Things technologies are monitoring the air quality, they're setting the temperature, and they may be turning on and turning off the lights automatically in the workplace. IoT devices are very convenient. They provide automation and flexibility of things that normally we wouldn't have access to. But they also come at a cost, especially from a security perspective. These organizations that are designing and developing thermostats, lighting systems, video doorbells, and the like are very good at creating temperature and video doorbells, but they may not be security professionals. So we do have to think about how we would implement IoT devices in an environment that is highly secure. It only takes a single IoT device to be exploited for an attacker to have full access to the devices inside of your network. If you work in an environment where there are large pieces of machinery, then these are probably networked together using SCADA. SCADA is the supervisory control and data acquisition system. Sometimes you'll hear this referred to as an industrial control system, or ICS. So if you work for a manufacturing company or in power generation, then you're probably very familiar with this type of equipment and connecting all of these devices together using SCADA. This allows the technicians to sit in a centralized control room, monitor the status of all of these pieces of equipment, and be able to make changes and modifications in the control room rather than having to physically visit every piece of equipment. One characteristic that tends to be very similar across many different organizations when it comes to SCADA is that all of these need to be completely segmented from the outside. You can imagine the security issues that could arise if someone was to gain access to power generation systems or oil refineries. This could have a dramatic impact not just on immediate power needs, but could affect it for a long period of time. This is why you'll find that many SCADA systems are some of the most secure that you'll find in the world, and for good reason. If you use Windows, Linux, or other operating systems on your desktop, your tablet, or your mobile devices, then you're using a non-deterministic operating system. That means that there's no single process that can suddenly grab all of the resources of the system and take priority. But there are some systems that need that kind of deterministic use. If you're driving an automobile using military equipment or setting up manufacturing equipment, then you're probably going to need a deterministic operating system. You may have already taken advantage of an RTOS or real-time operating system when you drive your car. If you're in a situation where you need to brake the vehicle very quickly, your entire system will suddenly focus on that braking system and make sure that you're not able to skid out of control. The anti-lock brakes kick in immediately, understand the environment that you happen to be driving in, and can safely bring you to a stop. As you can imagine, we are very sensitive to any security issues that may be associated with our real-time operating systems. We don't have the luxury of these types of operating systems able to wait around while something else is occurring in the operating system itself. We're obviously not installing antivirus or anti-malware software into our automobiles, but the same type of security concern certainly applies regardless of what system it might be. This is why those systems tend to be very self-contained, and it's very difficult to find a way in to even access the operating system in that equipment. It might also be difficult to gain access to an operating system that's running on an embedded system. An embedded system is one where the hardware and software are all created as a self-contained and purpose-built device. Sometimes we see these embedded systems working as single components that make up a much larger device. We also generally find that embedded systems are created for one sole purpose, and that's the only process that embedded system does. This would not be a technology where different apps might be loaded or you might pull in different capabilities from a centralized app store. Instead, these are designed to do one thing and do that one thing very efficiently. For example, the traffic lights that you see when you're out driving in your car are all controlled through an embedded system. The digital watches that we use today are very good at providing us with information on weather and time, and you'll notice that there's no direct access into an operating system on that embedded system. And in a doctor's office or a hospital, you've probably seen monitoring equipment for medical use, and that is certainly a very advanced form of an embedded system. One concern that most security professionals have is maintaining the uptime and availability of their critical systems. One way to provide this uptime is through the use of high availability. This gives you a way to keep a system constantly running even if one part of the system was to fail. This would be one step up from something that might simply be redundant. Redundant means that we have multiple systems available so that one system can be used if another one fails. But it doesn't imply that this system would always be available. You may have to pull a redundant system out of the closet, put it into the rack, power it on, configure it, and finally that system would provide some type of availability. We often refer to high availability as HA. So there may be an HA configuration for a pair of firewalls that you've installed. If one of those firewalls was to stop working, it would fail over to the other highly available firewall. Sometimes this high availability can be configured with additional efficiencies. In our last example with the firewalls, we had a primary firewall and we failed over to a backup that was simply waiting for that primary to fail. But some firewalls can be configured so that both of those systems are active all the time. And if one of those firewalls was to fail, the other would continue to work normally and all of the traffic would continue to flow without anyone knowing there was a failure. When you start designing highly available systems, you also tend to spend more money. In our previous example with the firewalls, we needed two separate firewalls to provide that HA capability. But if we have two separate firewalls, maybe we also need two separate network infrastructures. And if we have that, perhaps we need two separate power systems. You can continue to add on these systems and build out and plan for additional HA, but as you do this, there will be more and more costs associated with that. And eventually you'll get to a point where you'll need to make a business decision on whether you'll spend that additional money to be highly available or if you'll simply take the risk of that downtime.
All right. Any questions on that, guys? That one had a lot of information packed in there. All right. Oh. Awesome. So you have plenty of experience with this stuff. And maybe we'll have to refer all of our questions to you, Sally. All right. Well, we'll get started with this one. This will probably be our last video for today because this will end right before our time's up.
Okay.
And the last one of the infrastructure concept. So it'll be a taking off point. All right, here we go. Once again, let me know if you guys have any questions or want me to stop for any reason.
Okay.
When we connect to a website or start an application, we want to log in, run transactions, or use the capabilities of that website. We expect that those resources will be up and running, and we refer to that as availability. In the world of security, there's a bit of a nuance with availability. We want to make sure that our systems and resources are available, but we only want to be sure they're available to the right people. Information technology is very focused on availability. We spend a lot of money on purchasing redundant systems. We install very large and complex monitoring systems just so we can get information on how available our systems and resources might be. This is such an important metric that our success is often described as how much availability we've had. You'll often hear the summary of uptime described as a percentage. For example, our network has been available for 99.999% of the time over the last 12 months. Even with this emphasis on providing availability, there will still be times when a device or resource is no longer available. When that occurs, we want to know how quickly we're able to recover. This is probably one of the most common questions you'll get whenever you run into an outage or you experience downtime. The problem is it's difficult to determine just how quickly it's going to take to get everything back up and running. We have to first determine what the root cause of the outage happened to be. If hardware is our issue, we may need to replace that hardware. There's a process for that to occur. If the issue is with software, we would need to provide a patch or a fix for that software. And if there are redundant systems, we may need to install or replace those redundant components.
Confused about which IT certification to get? Let me map your path to career and salary growth.
One good measurement of resilience is MTTR, or mean time to repair. Whenever we're putting together a plan to install a particular technology, one of the very first questions we ask is, how much is this going to cost? It can be difficult to calculate this cost value because it's not any one thing. For example, we may have an initial installation cost, and that installation cost may be different depending on the platform that we're installing it on. Of course, once it's installed, it will need to be maintained, and there are certainly costs associated with maintaining that software or that resource. Those costs for maintaining may go directly to the manufacturer of the technology, or these may be internal costs that we have to cover. And of course, if something breaks or it needs to be replaced, there's a cost for doing that as well. And if you ask the accounting team how much this costs, the answer becomes much more complex. We have to consider depreciation if this is a capital expense. We have to think about the operational costs associated with this, and there most likely will be tax implications for all of those. Another important infrastructure consideration is responsiveness. When we send a request to a service, we're expecting a response back as quickly as possible. And as humans, we tend to be very sensitive if there's a delay in a response. This is a common metric associated with interactive applications where we're asking a request of a service and then we're waiting to receive the response. Responsiveness can also be challenging to quantify in some cases because there may be multiple steps that occur for a single transaction. That means that the responsiveness may vary widely depending on what is happening with that particular application. When we calculate responsiveness, we tend to look at the overall functions of an application. Some of those functions may be occurring very quickly and are very responsive, whereas others may require additional work, and it might take more time to receive a response from that app. Many of the applications we use may be subject to a different amount of usage depending on what time of the day it might be or whether it's the end of the quarter. If an application is highly used, we might want to increase the capacity of that app so that everybody can use that particular application without running into delays. We often refer to this as elasticity to describe how quickly we may be able to expand and contract the footprint of that application. You might naturally think, why wouldn't you build out the application to be the largest that it could possibly be? And the quick answer is that it costs money to have that type of scalability. One way that many organizations deal with that is to build out an application instance that matches the current load for that application. And then as more people need to use that app, we might extend or scale this application to be much larger. Sometimes this can be done automatically behind the scenes, and the end user has no idea that you're increasing scalability as the load increases. From a security perspective, we need to make sure that we're monitoring the entire application regardless of how it might scale. So we might have security tools that are able to monitor the base configuration, but we also need to extend those tools if we happen to increase the scalability and add more resources to that application instance. We often refer to applications as if they are one single thing, but in reality, there are many moving parts that make up a single application instance. For example, we might need a web server. That web server communicates with a database server. You're able to increase performance by adding a caching server, and to protect all of this, you might need a firewall. And those might be just the base components of any application instance. This may be a relatively complex implementation with tens of different components all working together. When deploying these applications, you not only need to consider the technical infrastructure, but you've also got resources on the hardware that's available. You might have certain budgets for building these out in the cloud. And of course, you always need to consider the process of change control. For many cloud-based deployments, this might be a relatively easy process. This may be completely automated through orchestration, which is a description of building out a cloud-based infrastructure automatically on demand. This is one of the significant advantages of a cloud-based infrastructure is that you can very easily and programmatically build out an entire application instance in a moment's notice. This is why project management and project planning is so important during the deployment phase. You have to consider where this particular application instance will be deployed, who will be deploying it, and any additional resources you might need. If any one of those happens to be missed, it's possible that this could delay the entire implementation. With the complexities and risk associated with today's technologies, it would not be unusual for an organization to want to transfer that risk to a third party. One common way to do this in the world of information technology is to take out cybersecurity insurance. One common use of cybersecurity insurance is to protect against ransomware. This obviously doesn't stop ransomware from occurring, but if your organization does have a financial loss based on a ransomware attack, you may be able to recoup some of that loss through cybersecurity insurance. This insurance might cover any outages that occurred during that particular security event. And if you do have some business downtime and financial losses, this might be able to provide some recovery of that financial loss. This might also help an organization to minimize the risk associated with what happens after a security event. It's not unusual for a downtime that causes financial loss to the customers to result in some type of legal proceeding. This cybersecurity insurance may be able to assist with costs associated with hiring a lawyer and dealing with that legal process. It's certainly true that the longer it takes to perform a particular task, the more money that's costing an organization. And that's why if you're trying to recover from some type of outage, you should already plan to have that outage recovery process be as efficient as possible. For example, let's take the situation of a malware infection. We know that this system has malware on it. We know that the best practice is to delete everything on that system and start over again. One way that you could do this is by reloading the operating system from the original installation media, and that might take as long as an hour. Or perhaps you've already made images of your systems, and you can easily recover from an image backup in approximately 10 minutes. Although both of these recovery processes result in the same working system, one of them is much easier to process and indeed much less expensive. If you're planning on implementing a new application or a new service in your organization, you might also think about what it will take to get this system back up and running if it runs into a problem, and find the easiest way to recover from that particular situation. They say that the only constant is change, and that certainly applies to the process of patch availability. We spend a great deal of time going through the patching process to fix bugs, provide security updates, or make our systems more available.
Roku Ads Manager puts Roku's reach within your reach. Sign up at ads.roku.com.
Usually, once we install an operating system or an application, one of the very first things we do is check to see if there are any updates before deploying this into production. And very often, we will need to install additional patches that were released after this installation media was created. In most organizations, this is a normal part of the IT process. We know that we will get monthly patches from Microsoft, and patches will arrive from other organizations throughout the month. Our organization, of course, will need to test all of these patches, make sure that it's not going to break something that's currently working in our production environment, and then we will need to deploy those to production as quickly as possible. If you're working for an organization that doesn't seem to have an emphasis in the patching process, then you might want to reconsider your security posture as it's associated with those systems. If you're not going to patch a system or an application, you leave it open and more susceptible for some type of exploit. And from a security perspective, we want to be sure to limit any instances of a security risk. But in some cases, you might find that an organization doesn't release patches and there's no process in place to patch that particular system. We see this often with embedded systems like HVAC controls for your heating, ventilation, and air conditioning, or it may be time clocks. These are purpose-built systems. There's no internet access or other type of connectivity to this device, so there's no way to easily patch what's inside of that embedded system. This is relatively short-sighted these days because attackers will find any technology and find a way to exploit that technology. There may certainly be security issues associated with the software that's running on these systems, but until you find a patch, it will remain vulnerable. It might be a good idea to provide additional security around this particular device. For example, if these devices are connected to the network, you might want to have a firewall between this device and the rest of the world, if only to provide another layer of security. One thing that today's technology can simply not do without is power. We must have electricity to be able to run all of these systems, whether it's something that is on premises or in the cloud. Unfortunately, we often don't think about our power infrastructure as being something that we might want to monitor. But in fact, it is one of the most important components of everything that we do in technology. It's often a good idea to bring in a licensed electrician who can look at your current power usage and give you plans for extending this power in the future. And those requirements may be quite different depending on what you're doing. For example, if you have a data center, your requirements for power will probably be very different than the power requirements for an office building. For most organizations, there is a single primary power provider for your particular geography. But if you're living in a very populous area, you might have multiple options for bringing power into your facility. But there may be times when primary power is simply not available and you may need some type of backup. In those cases, you might want to look at a UPS, which is an uninterruptible power supply, or something like a generator that can provide some or all of your organization's power requirements. In today's cloud-based environments, we tend to take the resources we need for an application instance and break them into their smallest components. One of the components that's going to provide the heavy lifting and processing is the compute component. This is something that's more than a single CPU, and in the cloud is probably called a compute engine. This is the part of the entire process that does the actual thinking and processing of the data. It might be a single processor running in a server that's in our data center, or it may be multiple processors that are located on multiple cloud-based technologies, and we're able to scale those systems to be whatever size we might need for the computing requirements of our applications.
All right. How do we feel about that? Any questions? I know, Sally, you were saying you're pretty confident about that. Sorry about before my internet kind of cut out for a second.
I don't have any questions relating to it.
Cool. Pretty straightforward. I'm going to give that spot for questions if anyone needs it. What'd you say?
But the topic of IoTs is actually a very hot topic nowadays.
Say it one more time.
Oh, sorry. The topic of IoTs are definitely a very hot topic nowadays.
Yeah, I've been seeing a lot about that. I'd like to learn more,
Yeah.
deeper about that.
Like, I would like to learn the infrastructure of like IoTs and in its security.
Yeah,
It just
I
seems
don't
interesting.
I don't know a ton about it. I don't have like any smart devices really in my home, so I've never paid too much mind to it.
Yeah.
But it is still something I need to learn, obviously. I mean, I know enough from like Professor Mister's videos and stuff, but it's definitely something I want to delve more into. So
Yeah.
I said good concepts about the hierarchy of how deep the chain ability go.
Well, it's like every Tesla you drive by. Those often have like IoTs inbuilt into them.
Yeah, right. Like the infotainment center and stuff like that.
Yeah. Smart
Yeah,
homes and
I've read a lot about those things. That's honestly part of why I haven't gotten
yeah,
a lot of like small devices like that with IoT in it.
yeah. Even
There's
medical devices.
consistent to measure how it's just like cutting off like that.
I like to learn more about that.
Yeah, there's a lot of stuff that's what I love about the field is everywhere you look, there's always something
Yeah,
that you can learn, even if it's something you've learned a million times. Just like, oh, there's other details about that I didn't know.
yeah. Well, it
Sally,
all
you
ties
said
into the foundations.
yeah. Sally, you said you've been working with this kind of stuff for a while. What have you been doing for work? Oh wow, that's really cool. You've done a lot of cool stuff. I'd love to hear some stories sometime.
Oh, spaceships.
Yeah, right.
Yeah, that's something.
Oh wow. So you've got
Oh,
a lot of
NASA. That
experience
explains
there.
it.
I actually the deep base probes, not quite the same, but I heard an episode of Darknet Diaries recently where they were talking about building data centers under the ocean, which sounded really cool.
Oh, really?
Yeah, I guess because of it being underwater, the energy and omission issues are much lessened. Um, I'd love to look more into it because she only really talked a little bit about it. There's definitely a lot more to learn about it, but it sounds really cool. She said they're in these containers on the ocean floor,
Yeah,
and it helps to keep everything cool. The dust
I was
and
gonna
stuff
say.
isn't as much of an issue, and it just is longer lasting and more effective.
Yeah,
Which
sounds more efficient.
that's what they were saying. I mean, it sounds like it's a probably a higher upfront cost, but then it's one of those things where once you do it, you're probably much better set for a while.
Oh,
Voyager
for
probe
sure.
that worked on is still operating. That's really cool, Sally.
That's really cool.
when your mic's working, you're gonna have to tell us more about that.
Yeah.
But I'm gonna stop recording here.